This is The Packet Pushers, the gentlest and most humbly understated podcast ever on data networking, because real engineers get together to talk nerdy about networking. Located in the hot aisle, perched on top of the power-sucking core switch, one row over from the rack you use for experimentation on executive leadership, is where you're going to find us. Packet Pushers is a place where no one has to speak in terms of business people understand, where nerdy is the normal, deep dive is the baseline, and you can smell the fumes of virtual whiteboard markers in your ears. Today's show is sponsored by Talari Networks, and the topic du jour, mon frere, is software-defined WAN, painting lovely pictures all over the virtual whiteboards with a big cloud in the middle marked WAN. And our network canvas starts with our usual roster of guests, but the most important person with us first is Mr. Banks. How are you today, sir?
I am not the most important person, but I am flattered that you would even suggest such a thing. My word, I feel just awesome now. Wow.
Is that right?
Yeah. Oh, you boosted my ego so much you have no idea.
Really? I'll have to fix that.
Yeah. Well, before the show started, you said you were going to slap me in the kisser the next time you see me because of the rude comments I was making to you.
Yeah.
So
in the kisser, not on the kisser. Stop getting that idea. Yeah.
Right, my apologies.
This is getting a little awkward here.
Joining us today is also John Dickey. John, please tell people a little bit about yourself.
Hello, everybody. My name is John Dickey. I'm CTO and co-founder of Talari Network.
I guess the best part to say is about where we want to start off is introducing Talari Networks to the audience today. Now, we've talked a bit about software-defined WAN already, and there's three things about software-defined networking that get me excited. One is the ability to cut costs in the WAN, the ability to, from various different means, whether you want to use internet or whether you want to, improve performance or whether you want to be able to use multiple different links. You can fundamentally just cut costs. And the second thing is you can actually make changes on the fly. The advantage of this software-defined WAN is instead of fiddling with autonomous routing protocols that eventually converge and you have outages of, well, who knows how long, usually seconds, but can be hours when you muck it up. This environment helps you in that thing. And the third part is you can actually see what your network really looks like because you can't SDN it unless you actually controller can actually see it. So they're the three things that get me excited, but we have a whole bunch of other questions. So John, first kick us off and tell us what Talari does.
But we're an overlay solution that it does a network-wide, international or domestic or whatever, and each node is working collaboratively with each other, but they're centralized controlled through what we call a network control node, which is much like an SDN controller. We do this at an architectural level in terms of administration, and that gives a lot of intelligence network-wide, and then each one of those nodes is hyper-intelligent in terms of the situation on the ground, and so they're able to take care of per-flow packet sessions and make sure they do a best mapping to the underlying capabilities of the networks at that moment.
Okay, so smart WAN then. This is an overlay on top of a wide area network that someone's already got. They've got a WAN. They need to make it more capable, make it easier to use, different links as the case may be. You put in Talari, and then you guys are monitoring what's going on the wide area network and automate using the best links.
Yes, exactly. I always use analogies, and I apologize if they sometimes are a little laborious. I think at FedEx, no one ever thought you could do overnight delivery until FedEx decided to do it. They actually got a C, I think, on their paper in their MBA course. But the fact is, by us measuring every packet, we basically stick it in this envelope and we send it across, and planes, trains, or automobiles, one way or the other, package gets delivered. Well, the same thing for us, right? We view MPLS like a railroad. Service levels are in MPLS, and service levels are in railroads, and the interstate's like the internet. But I can still get my pizza hot when it gets delivered to me because they have intelligence to figure out how to get from point A to point B using the diverse paths available between that pizza shop and my house. Well, I do the same thing here. By having intelligence, by tagging and empirically analyzing every packet that comes across the network, and then doing statistical models, I can basically anticipate the next 100 milliseconds. And by doing that, I have the ability of making very smart decisions. It comes to what type of traffic I'm trying to deliver. So if it's voice traffic, obviously I want lower latency, lower jitter. If it's bulk traffic, well, higher latency is okay. And even if there's a little loss, I can probably use that too.
Some people listening to this might go, it sounds like hybrid WAN to me. Is that all this is, or are we talking, because we've been saying software-defined WAN. Is there a distinction we want to make here between hybrid and software-defined WAN?
Hybrid WANs have existed for a long time. You can get a Cisco 1841, right, and do some IPSLA steering, maybe a pin track up there to make sure the link's healthy. And if it's not, then 6 seconds later, maybe it'll fall over after 3 misses, right? You can do those type of things. And that's been there at least from the late 90s, maybe even before that. Nothing new there, and that's actually a pretty viable solution out there in the world. That's not what this does. This is a much more centralized intelligence in terms of how you policy administer and how we monitor and how we actually can use this data that's on these devices to make strategic buying decisions for your long-term vision of your network and frankly, your user service level. Yeah, hybrid WANs are good. That was yesterday. This is today. And the more intelligent layer that can exist only because right now we're in the day of Moore's Law where my processors are pretty big on Intel, right? And I have dense cores and I can integrate more service chain in one product. As well as disks are cheap. I can use SQL to do my analytics. I don't have to live with the ASIC world of the past. And that's what hybrid WANs were then, but this is now. And
the x86 processor, this is a commoditization trend as the market has built more and more x86s. Now we can start to use x86 in, that reduced the cost of the x86 to the point where it's now cheaper to use a general purpose CPU to run networking assets than it is to go and buy a MIPS or an ARM or whatever it was we used to use in the old days.
Yeah, I mean, I don't necessarily need a CAM for everything, at least around the WAN. Obviously, in the core switch, it's a different story, right? I mean, we know that. But, the WAN, when I'm accessing and I'm putting a gig up there, you know what? Intel's pretty damn good right now. And then as AES, Intel's got AES acceleration into their instruction set. So you have that. Memory's cheap. Disks are cheap. This didn't exist. You wouldn't have been able to do this solution. I contend, at least, you wouldn't be able to do this solution in 1996.
So AES, you're talking, what you're saying there, let's just drill into this because I think this is important. Encryption in the WAN is becoming an increasing issue. Mm-hmm. So for the last 30 years, we've just assumed that the WAN is secure. But what we know now is actually it's not. That it's trivial to listen in and record WAN connections. So if you buy a private frame relay or a private ATM circuit, you've always never been able to encrypt it because the requirements, you needed to have special chips in special routers with special software. But now what you're saying is there's an AES processor in the Intel CPU?
Yeah, well, there is an AES acceleration instruction set in Intel CPU right now, at least the higher-end ones. Even some of the Atoms, they've actually put it in there. It's pretty standard. Actually, VIA, the cheap little VIA processors, which were Intel clones, even had it at one point. So it's becoming more and more. By the way, it's also acknowledged, AES ain't triple DES, right? Triple DES was extremely painfully slow. AES was designed not just to be cryptically strong, it was also designed to be efficient in terms of its processing. So yes, doing encryption does have a certain performance impact, but for us, even for large packets, which is where the encryption is going to hurt, it's about 12 or 13%. It's not that bad of an overhead considering what you get, even on the private circuits. The other thing is when you actually have diverse circuits in front of you and your application is being utilized across those circuits, depending on the type of application, you can't reassemble all of them on any one link if you happen to tap into it. So that provides just an additional level of security.
So you're talking about spraying those session packets flow over multiple links if you have them.
Exactly. So just using standard off-the-shelf equipment with, frankly, very special software, which is what we do, we can do things that weren't possible 10 years ago. So
there's a few different parts about that process. Let's just very quickly drill in. I've got an existing WAN, but I don't have to replace anything. I don't have to, or I could do?
You don't have to. I mean, we start out as an overlay similar to like a WAN-op solution, right? Put us fully in line right in front of that router. They think they're talking to the router. We just happen to pick up packets of interest and do our magic. On the other hand, if you want us to be more in the hop, then you can make us the gateway and we can do all the things like a IP forwarder would do in that situation. We have route tables and such. Mm-hmm. But in general, most people don't want to have to forklift up their branch office, right? They don't have the IT guys out there. They send out the box, they plug it in, they do the physical layer, right? They upload a file to the console and then next thing you know, he phones home and everything's good. So it's easier to put it in the overlay fashion for most branch offices than do anything more elegant than that. In later on times, if they want to eliminate another hop in that service chain, go ahead and take out the ISR. But they don't have to.
So when a customer's got confidence that your technology is doing what it wants, they might want to pull their router later.
Or they may actually be using other services in their router. I mean, they may have an ASR blade in there that's doing some DNS serving or something like that specific to their purpose. I guess I kind of view us as a guest in the network's house, right? We shouldn't go in there and insist they move all the furniture just because we happen to show up. If they have an ISR, fine. Go ahead and plug us in front of it. If they don't want to have that ISR, then go ahead. We can probably serve that purpose as well. The firewall is the one thing we don't integrate right now because we just think that's a religious issue. That, be careful of people who are checkpoint people or Palo Alto people. They're really good at their job. We do have the ability of going directly to untrusted segments, but we don't permit any protocol but our own. And there's reasons we do that. We deny all. except for our own encrypted, and by the way, only encrypted protocol. We do not let any user data ever hit an untrusted segment if it's not encrypted.
Just to drill in on that, you're saying the Talari appliance, for lack of a better word, at the moment is not going to act as a firewall. You're not tracking state. You're allowing your protocol, whatever it is that flows in between Talari nodes, and that's it.
Yeah, we do not do the security policy in the Talari appliance, but we do track state, obviously, for your application sessions performance. That's what we do for a living. But no, we are not. There are some people who can do the security policy administration, and frankly, I look at it as, you go in there, and there's always that quiet guy in the back of the room. And, you walk out later on and says, I'm not going to replace my firewalls. And so for us, we've chosen to have us sit in front of the firewall, let them administer the firewall. But if you put us in a non-trust segment, we can still utilize that bandwidth. We're just not going to let you go unencrypted out there and surf the web with it. We'd rather have a firewall in front of us to do that, and a trusted firewall.
Okay, I want to go back to one of the earlier things we were talking about here, because the point of software-defined WAN, all of these solutions that we've talked about on Packet Pushers, and you guys as well, private WAN and then public WAN and then combining the two. You kind of describe that as your value proposition and make that transparent to users. And implicitly here, we're talking about cost savings. So we're talking about cost savings from an x86 standpoint, and we're talking about cost savings from a WAN standpoint. Hey, I can use public internet transport as my as a legitimate WAN link between offices now. Really? Because that seems to me kind of optimistic. I've asked this question, and I don't know that I've gotten lots of answers I love yet. But here's the thing. If you consider traffic flows that need really specific network guarantees, like voice traffic, right? You got to deliver that, and it's jitter sensitive, and so on and so on. How can we say that the internet is a viable transport for businesses? What is Talari's take on that?
Yeah, it's interesting. One of my inspirations when I started the company was a good friend, and too bad he lost his job soon afterwards, but that he decided to rip out MPLS and a hybrid ATM network, actually, in some parts. It was a chip company, and put IPSec VPNs in. Mm-hmm. And since then, every time I meet customers, I said, friends don't let friends drive on single-link IPSec VPNs because it didn't work out well, right? I mean,
you said something really key there. You said single-link IPSec
exactly.
VPN. Okay.
Exactly.
I think I see where you're going.
Yeah. It comes down to when you have information and you have choices, you can make intelligent decisions, especially if you have very timely information, right? Instantaneous if possible. What we've noticed is that diversity is a virtue, and we need to judge the network based on the character and then take advantage of that diversity. So, yes, if you're going to do a single-link IPSec VPN, you can put us on there. By the way, we do some good things there. We can do some retransmission. At least we can identify when the network's the issue as compared to something else, to troubleshoot the heck out of things.
You're talking about if someone's using IPSec VPN as a WAN link today?
Exactly. But if you use us in that type of single-link solution, we have some advantages. But truthfully, we are really strong when it comes to diversity. And if you put two, let's say, broadband links, best effort broadband links on it, we actually can do, in our overlay, the monitoring of it so we can instantly adapt to when there's an issue detected and mitigate around it. But we don't just mitigate by steering the traffic around. We actually can retransmit traffic that may have been lost on the link because we identified it and detected it so quickly. We use queuing theory. We don't use Gaussian statistics. We use queuing theory and Poisson distributions. And because of that, we can pretty much call the network in 2 or 3 packet times if it changes its behavior. We also combine that with first and last mile bandwidth reservation. So, typically in the internet world, right, someone's sitting there and next thing you know, Microsoft does an update, right? And next thing you know, everybody's web surf goes down. For us, though, what we're doing is bandwidth reserving on that last mile and make sure that everybody behaves well. Even with the internet traffic, we do policing on WAN egress, or what we call WAN egress, but it's basically last mile. As well as we do in our overlay, which we call conduit, we do first and last mile synchronization. So you can't overrun, right? It's like X on, X off. Remember all that used to happen? You can't overrun the last mile from the conduits on the first mile. They'll back off on the on-ramps. Combining those things together, diversity, instantaneous measurement, and first and last mile bandwidth reservation, negotiation and reservation. So, those types of things come together to make the internet much more reliable.
You're saying first and last mile because the deal is the middle part you don't own, and you can't actually reserve bandwidth end-to-end across that circuit that you don't own if it's public internet transport. So what you do then is you say, I know what my first mile circuit bandwidth is and the last mile where the destination is, circuit bandwidth is going to be, and I know I need X amount of bits for this data stream to go through, and so you reserve them, on each Talari end, and then you basically got this tunnel through the middle section that you can't do anything with, but you have a pretty good idea that it's going to get there on the assumption that nothing in the middle is dropping traffic. So that's where your bandwidth reservation becomes meaningful. No, it's not a true end-to-end bandwidth reservation, but effectively, it's statistical analysis that you're using to pull that off.
Exactly. I'm going to get a little zen here. I call it control, influence, and adapt. You can provision on the first and last mile bandwidth allocations what you believe fair to be on the shares. Minimum reserve, maximum reserve, and stuff like that. So you can control that as far as we're concerned. And let's hope that router in front of us isn't oversubscribed, if there is one. But that said, then there's influence on that last mile. For example, I talked about using progressive red when someone's downloading that virus update. So I can keep that reasonably well behaved by influencing. But in the middle of the internet, frankly, it's adapt, right? If it's raining outside, I got to get an umbrella. Okay,
so what you're saying is you're not just what we normally do in normal traditional networking. I'm going to call it traditional for lack of a better word, or legacy networking. Never seems to have the ring of reality around it. But you're saying that I'm actually seeing each flow or a group of TCP flows, identifying them and then saying, this is something coming from the internet. I can say something about it. I can say this is non-critical, so I'll use random early discard to throttle it so it doesn't override. But there are other flows in the network which have different criteria. You want absolute priority, or you want to do flow management, but not necessarily with red because you don't want to incur packet loss.
Well, in particular, if stuff's coming across our conduit service, right, we basically have a first and last mile synchronization. The people sending, it's like when you get on the interstate and there's that little light that kind of flows you off on the on-ramp. You basically don't want to congest in the middle, and you don't want to congest on the last mile. So the first mile will say, hey, I got bandwidth. I need more bandwidth. He then negotiates with the last mile, and the last mile says, okay, that's on demand. I'm going to allocate more bandwidth for you. It's like RSVP, but it's the first and last mile synchronization. Now, there may be other contenders for that. It could be that there's maybe some internet circuit there that's going to a non-Talari site, or it could be there's internet access and they're surfing the web on that site. But we will do fair allocation from that and make sure everybody stays reasonably well behaved, because we don't want, especially voice over the internet, we don't want that last mile to get congested. No one wants a traffic jam going in for
now, voice over the internet. Now, I've got a particular bugbear, and no doubt listeners would have heard me go on and on about how voice isn't mission critical. And most people would say voice over the internet can't be done because you can't get reliable jitter and delay. Now, I know companies that have been running voice over the internet for more than a decade, which puts the lie about what most people believe. But you're saying, again, voice over the internet. Now, is this real?
Yes, it absolutely is real. I mean, actually, truthfully, I'm with you on the voice over the internet is legitimate. I mean, Vonage has been doing it for a long time, so it's not new. There's a difference between consumer grade and enterprise grade. But I also will tell you that probably the most unpredictable part of my drive to work in the morning is getting through the cul-de-sacs to the interstate. We do a really good job watching in those neighborhoods, right, the first and last mile through the alleys. Then we take care of that, and then, frankly, voice is very good for an enterprise application. Of course, broadband is way better now than it was even 10 years ago. We're not sitting here with 56K modems. So more is better, and that is true. But measured intelligent more is even better again, because we want to provide a service level. And the other problem is this. I mean, quite often, let's say we can't. Let's say all the networks available to us, despite all the diversity and all our measurements and all our intelligence, there's just too much traffic jams going on. At least we know where the problem was. We're not sitting there trying to figure out, okay, I'm going to go packet trace here or there. It was an incident. I have these SQL databases that measured everything. And from these SQL databases, it's like a black box in a flight recorder, right? I can actually pull it up and say, hey, guess what? The problem's within the WAN, the problem's not within the WAN. And that, frankly, it's just mean time to problem resolution. That helps a lot of people out. And actually, quite often, our network devices are used for that purpose to a great extent, even in that economically non-viable locations, because they like the idea that they can just solve the problem faster.
Yeah, you've been talking about the speed at which you can measure things and gather data and then react to them. And in fact, you even talk about real-time measurements on your website. How do you pull that off in an environment that is just by definition, it's got some latency and so on?
Well, real time's all relative, right? Let's just say as instantaneous as humanly possible across a latency-based network. Our patents are around what a video buffer is, right? In a PC, right? You write to a video buffer, next thing you know, it shows up on the screen through the adapter card. We basically created the equivalent of network memory that's like a video buffer. So each box has a little memory window in which it writes to, and then the other boxes, its peers automatically get synchronized to that data. So there's a read window and a write window, and that's part of our patents. Now, what we do inside the product, and actually we do this also for voice, by the way, if you turn it on, is we can redundantly transmit that across the two lowest latency links. So we try to minimize the time it takes to get to the network. Now, on the other side, we squelch the redundant packets. We don't need to send 2 packets downstream. But for voice, for example, we don't want 2 packets. But, when absolutely positively has to get there overnight, do you send it to FedEx or UPS? We'll send it both. Why not? And then throw with the second one.
Well, and there's a trick here too, right? Today you're using FedEx and UPS because they're the best. But sometimes you want to have a third supplier because they're half the price of those two premium services.
Agreed. And it's interesting, too. If you use FedEx, UPS, and let's say DHL, to send it up, FedEx may be better going to the West Coast. UPS may be better coming to the East Coast.
And you can play them off against each other.
Exactly. So
today, most people in a WAN contract aren't able to get – you can't compete. You can't compare apples with apples. You can't have – Verizon offering you a service and Telstra offering you a service because you have to bring in a tail circuit, or you can't shop them against each other because once you've got their service, you're sort of, everything has to be on, even have to have redundant circuits on one provider so that you can fail over from, there's all this hassle. You cannot actively negotiate for bandwidth competitively between the two.
So with us on the state instantaneous sharing, when you have information, and I go back to it, it's just like Google Maps when you're driving to work in the morning, you see where there's congestion points and you avoid those. Well, we have this memory buffer and we basically create the network map. And that network map gets reflected instantly. Now, if there's a critical update, it gets reflected faster. If it's non-critical, we'll just refresh once it's half a second or so. And that gets reflected over, and then we can adapt the network application steering, and basically using all the network if possible for some applications, but we adapt those things around that refresh. So that's how we do the instantaneous. In terms of the brokering of the network behavior, I got to tell you how often we go into a customer and they're like, I love my MPLS, love my MPLS, love my MPLS. Of course, they bought the MPLS, so that's why they love it, and they don't get in trouble maybe. But especially for international, I go back to it. Railroads are reliable. They have a pretty consistent service level, right? You know when the train's going to arrive, and hopefully when you'll get off the train. Nothing wrong with railroads. But the internet quite often, and the interstate quite often, can be faster, especially international. You have a lot of fiber under these oceans that's long, and you don't have a lot of hops in it. Not a lot of train stations in those internet circuits. So as a result, the latency, frankly, from US to India, very often, about 90% of the time, is superior on the internet path than it is on the MPLS circuit. In the other direction, and usually, by the way, around some rush hour times of when they're surfing the web at lunch or something, then the internet can get a little clogged up. But in the other direction, it's almost always better from India to the US using the internet as compared to the MPLS. And people are always shocked. They call us up, it's like, why is my voice seem to migrating always to the internet? Because it's better. We don't judge the network based on who you bought or how much you bought it for. We judge it based on its character of jitter, congestion, latency, packet loss, and availability. And, it's a character thing. And then we will use the best character network for your application requirements. One other little thing in terms of brokering that we build all this data, although we do this instantaneous updates and we can remap around it. We also build this into the SQL databases, right? So we have this over long periods of time. And then we aggregate all that up into a analytics package we call Aware that then lets you plot this over months or years. And then you can go back to your service provider. We call it the Talari discount. And you say, hey, listen, the internet's cheap. The MPLS is expensive. Why am I buying the MPLS? Because the internet seems where my applications like to use it.
Yeah.
Next thing you know, you have buying power. It happens quite often, actually. You'd be surprised.
And the thing is that, 10 megs of dedicated WAN, private WAN, is you can buy 100 meg internet.
Exactly. Now is 100 megabit Ethernet is reliable in all times? Maybe not. But, for the certain times when it's not, we seamlessly migrate away from the issue, right? We see it coming. It's just like you're driving down the road, you see there's a little jitter. When I see jitter showing up ahead of time, I know the network's getting less stable. So I will gradually move things away from
So you would have multiple, you would recommend a company to have, say, 2 internet links and a private WAN link coming in, and just load balance across all of those as a baseline? Or is that an initial discussion point? I mean, that's not a hard and fast rule, but maybe
it's a very common deployment for us, right? Usually it starts out with they already have a T1 or E1 out there, and they have a backup IPSec VPN, which is ironic because the IPSec VPN is 10 times as fast as but they don't use it, right? It's active standby. So it'll put us in.
That's a perspective thing, though, right? I mean, the network guys are always, from a standpoint of, I have a guaranteed pipe. It's a smaller one, but it's guaranteed. I know what kind of service I'm supposed to get across that. I guess you're kind of challenging that and saying you have a smaller pipe and maybe the service isn't as good as you think it is.
Yeah, and when it's not as good as it should be, then we'll move you away from it. What we want to do is protect the vital organs, though, right? Well, let's say something bad happens on an internet circuit. It kind of goes down. It gets brown. So what you want to do, though, is protect the vital organs, right? What are your critical applications? And inside our rules, this gets where the SD part of the SD-WAN starts applying. In our rules language, just like a table, it's like an SDN table, you basically specify, this is my vital organ. Now, it's not always voice, Ethan. It could be your SAP SAS or something like that. You can tell us what it is. We have defaults, but you can override those defaults. And from that, then we will protect the vital organs. Of course, your rsync backup will take a little longer now because you don't have the big pipe. But the critical traffic that you have will be taken care of.
I mean, now, there's obviously a controller in here. Controller's not in the critical path. And this is one of the most common criticisms of SDN is that the controller's a weak point. Is it?
We do what I call a 4-tiered model. Now, the first tier, obviously, is the administrator. No one ever thinks about the administrator, but he's a decision maker too, right? You got to put him in. He's the one worried about the corporate vision and how to get the best return on the investment of the enterprise. But below that, we have the aware node. The aware node does, again, the long-term analytics and the buying decisions and also the policy administration. Then you push it down to the next tier, which is the network control node. The network control node is typically in a hierarchical type of fashion. It provides common clock sync and policy mapping. And also, sometimes it's the controller for it's kind of like DMVPN, but we call it dynamic conduits that allow these multi-links to come up on the fly without having to reserve the bandwidth ahead of time, right? When we need the service, they come up, we reserve the bandwidth, we measure the quality of the networks between the peers, and we do that. So he does that type of control, but that is at the pipe infrastructure. Each node in the network is empowered on the ground. The commanders on the ground are allowed to do what's right for the platoon. And so when they detect the network's a little wonky, they will adapt themselves, and they'll do it rather quickly. But they'll do it based on the policies that come down through that hierarchy. So the hierarchy is the centralized authority, but the distribution is the actual intelligence. And that's how they can do it instantaneous. Now, it works the other way in the other direction, though. As we do these behaviors, we're recording what we did, and that percolates back up, eventually to the aware node, and then also to the administrator, so we can make the strategic buying decisions that he should make. Does that make sense?
So there's a feedback loop, I think is what you're saying. You're saying
exactly.
That there's an administrator, the administrator talks to the application, which brings me to my next question, which is about visibility, right, in a minute, because if you're saying I'm going to do all these wondrous things, I'm not going to be doing them. There's got to be a way to make this easy enough to use. But that's in a minute. The application will then drive the configuration into the controller, which then pushes it out to the devices. Now, the devices aren't dumb. They're not just programmed with a rule, flow left, flow right. They've got some autonomous capability in their own right. True? Absolutely.
And I know traditional SDN says you should absolutely separate the controller from the forwarding element. I know that. But truthfully, we're talking Intel architectures here. It's another process.
We're talking WAN because the controller's not right next to where the device is. It could be 3,000, 30,000 miles away. You're talking about a feedback loop inside the device where the network goes down. You want to be rediverting flows in less than milliseconds. To do that, you can't do that if you've got to go and chat back to the controller. And if the controller disappears, the device is going to be dumb. So clearly, it's not an option.
The analogy I use is if I touch a hot burner, my hand's going to move. It's not because my mind had to get involved with it. I have a ganglia, a little intelligence in my wrist that actually detects it, and it's a reflex.
Yeah.
And it
detects pain before your mind does and pulls your hand off. Right?
Exactly. And so we need that. We need to push that instantaneous decision making, not the strategic decision making, but the instantaneous decision making down at the edges to avoid the latency. Now, let's also make sure that the decision making has to take into account information base. It's not just I'm going to take this application and send it to this destination. Unlike the SDN in the data center, right? SDN in the data center, I don't want to be overly simplistic on this, but the SDN in the data center, the pipes are almost infinite. Right, in terms of the size, right? They're virtual pipes sometimes. The latencies are really low. Bits don't really cost that much because it's just a switch. In the WAN, no, the pipes are not so reliable. They have jitter, latency loss, and they have some cost to them, right? I mean, it does cost money to use these things. And at the end of the day, we have to make sure this is a slightly different approach to this. We need that information to figure out how to map the flows appropriately. Without that real-time information, the flows won't get adapted in an optimal way. And it's changing. It changes quite often, frankly, in the network. Okay,
so you're saying the devices themselves they've got some capability to operate using some sort of configuration which is deployed from a central node. Exactly. So it's not like the devices can't work without, if the WAN connections are all down, the node device can't do anything useful, but it's not dead. So if you lose a link, a 1 or 2 or 3, or it falls out of contact with the controller because the site with the controller node out, devices continue to work. The world hasn't ended.
Exactly. And exploring the controller, but one point also to remember is it's not just blackouts. It's brownouts. It's the network is just crappy, but it's not so crappy that we couldn't use it for some things. I like chicken wings, right? Chicken wings used to be thrown away as crap food, but actually they're not. They're actually pretty good if you put the right technique and sauce on it, right? Even a brownout network can be very valuable for some applications. I don't want to put my voice or my telepresence across it, but if I can detect it, I can still utilize the lower quality bandwidth for valuable purposes. And so that's one thing that we have to be sensitive to. We don't just say use it or don't. We say use it for the right purposes.
Okay, so the administrator sitting in front of the console now, how do they make decisions? Because if I'm starting to say, you were saying to me, oh, you can do this, and you can do that flow, and you can detect this, and if you got voice, and I'm sitting here, and I might be sitting here thinking, oh, how many access lists have I got to configure, and what happens if they change, and what happens if I bring in a new voice system? Does everything? There's got to be a visibility tool involved.
Yes, there is. And so there's aware. But before I go there, one second. On the network control nodes, right, you talk about the controller if a controller goes down. One of the things that we built in very early in the product is the idea of redundancy of the network controllers. So we can actually run, it's kind of like you cut the head off the worm, it will squirm for a while, right? I mean, but we can run pretty well without a controller. But that said, we also built in a diversity controller that they're high available to begin with on the premise. But even more than that, you can have a disaster recovery location with another controller. If a client, we call them clients, those are distributed nodes at the branch offices, if a client can't reach the primary network controller, he will phone to the redundant one, who will then do a proxy if the primary is still up. So he'll actually proxy for it. But if the primary does go down, he'll just take over. It's like the console comes from the ridge into the engineering, on the enterprise when they get attacked by the Klingons. So you can go over and man the entire network from that redundant disaster recovery site, and that's instantaneous. They don't even need to see it. No one's affected. No one was hurt by this. So that's what we do there. Now, in terms of the network administrator, for us, it's really important that the network administrator needs to see the network and administer the network the way their vision is for the network. I always laugh when I look at the access control list and it says, access control list below 100 because it was on the cam on the card, right? I mean, a lot of times in those CLI things, there was no abstraction between the hardware and how you configured it. For us, we don't believe that needs to be the case anymore, especially in the age of NFV. So we believe that you should view the network architecturally the way it's on your wall. It's a Visio diagram. So we want you to architecturally administer the network, including your applications and your sites and your leads and feeds. But you shouldn't have to get into the details of how my CAM is developed. And so we keep that at a very high level. The other side of that, though, it's just like if you've ever been a programmer and you do a high-level programming language, you want to debug it in a high-level programming language. You don't want to actually have to look at assembly code if you wrote it in C, right? That's really tough. I've done it, but it's really tough. Well, same thing here. If you want to analyze the network, you want to see it in the same architectural abstraction that you designed the network. I call it's kind of like a WAN CAD, right? You want to crash the car or see what happened to the car, right? It looks like a car. You don't want to have to go figure out what the atoms look like at the bottom. So you want to look at it as the same level of abstraction as you created it when you're trying to troubleshoot it. And that's what we do. And then you also want to expand across the time domain. You want to be able to look at it over months and weeks and months and years if necessary to figure out, are you making the right business decisions in terms of the application utilization of the network and the underlying network's capabilities to provide services to your end users. So we try to provide that at a very high level in the Aware product. And then, and I think that's important because frankly, there's just not enough people who can go per hop and try to configure this stuff in the gory details that you described.
No, it's funny. I'm just reflecting as you're talking. I'm reflecting on all the WAN work that I've done in the past and setting up QoS policies and what the failover scheme is going to look like and so on, and remembering how painful it was. In fact, I was talking to a guy I used to work with and for back in the day, and I was sharing with him, we could redesign that whole thing to be easier this way because we'd come up with a solution, 3 years ago, and it was painful, and it's still painful to administrate, and there's better ways now. And automating it is even better when you can take away the line-by-line and device-by-device configuration of complex routing policies for the WAN.
I mean, we've all done it. You ever have an IKE phase 2 failure and don't know what's happened? I mean, in terms of just getting IPSec tunnels up sometimes between site A and site B. Having a centralized administration there at a high-level architecture, I have 4 or 5 links to each one of these sites, right? Each one of these is going to have security policies going across it, right? Could you imagine having to configure each one of them by themselves? By the way, 4 links on one site, 4 sites on another site. That's 16 different paths. That's a lot of configuration just for 2 sites. Yeah. We support networks in the hundreds that work collaboratively with each other. We literally did try in the very first version prototypes to try to do this in a traditional per-hop CLI approach. It was not possible. There's just too many things that you would have to knob turn and set on each appliance for them to work collaboratively with each other. So when we threw it away and we said, okay, let's go centralized. And we did the centralization, we did it at architectural level, and then I did the decomposition through what we call configuration compiler. It's got hundreds of audits and stuff like that does static analysis to make sure you don't shoot yourself in the foot. And then those things get automatically propagated down to the ganglia, i.e. the client nodes of their own sites. And then those things worked together because they're already started smart. They started up smart because they're aware of each other. Now, because they're so smart, they can synchronize this real-time data faster. They're not exchanging, oh, what links do you have? What links do I have? No, they already know about everybody. So now all they got to say is, that network sucks right now. Why don't we move over to the other one? And they automatically get that with very efficient protocol. That's where it gets back to the real time.
And that's something we're not doing today with any of our existing. I mean, it's important to draw this out. There are people sitting there thinking, well, with OSPF or whatever, all OSPF or, our current BGP or MPLS says this circuit is up. It doesn't say this circuit's got 50% packet loss and you should be sending 50% less traffic down it.
That's right. That's right. They don't do lousy well. They don't do lousy well. They just do up or down.
It's best and only. Again, it comes back to this fundamental idea of IP routing defaults to best and only path, and there can only be one path. You can't load balance across multiple. And if that one path that you've chosen to route to at an IP level, which has no awareness of what's happening on the network or whether packet loss or extra jitter or, delay is happening or there's packet retransmissions happening somewhere or, whatever it is. But you're saying your devices can recognize this and adaptively cope with that and start to do more intelligent things like saying, there's a second, third, fourth path out of here. I'm going to shift some of these flows over to there.
That's right.
And, hang on, that circuit's now come back to life. The brownout seems to have gone away. Let's start sending traffic back down that again. And that all just happens automagically.
And it does. And I may have actually been using the brownout path maybe for some bulk traffic because, frankly, it wasn't that badly affected. And if I got a little loss, I can kind of retransmit myself because I'm aware of that application being able to tolerate some jitter. So I'm aware of the application's ability to tolerate jitter, latency, and some loss. And so I can adapt the underlying network mapping to their capability of handling that type of network. On the other hand, for voice, obviously, I don't want a lot of loss, and I don't want a lot of jitter, and I don't want high latency, so that I'll seg off of it. But I try to do it as seamlessly as possible. I don't want anybody seeing it, which is why, there's some videos of me pulling cables. But actually, the brownout situation is actually much more interesting.
Well, the thing is about a brownout is it's a thing that gets you a call that says there's something wrong with the network, and by the time you get there, it's gone away.
Exactly, which is where the FedEx thing comes in, which is you got to track your package, right? So the package didn't get delivered by 10 a.m., so you go to the website and say, where is it? Somewhere in Tennessee. So for us, we tag every packet. We're not probing. We're not doing round trips either. It's all one way. One of the things about the network control node for us and our SD-WAN play is time. Talari is about time. Time sensitivity in a global network clock that is at a microsecond resolution is critical because I need to be able to say when I go from point A to point B. My drive to work in the morning is different than my drive home. Well, I don't measure it by driving round trip. I need to be able to figure out when I send a packet across from point A to point B, if it didn't get there on time, I need to react to that rather quickly. And I can anticipate that ahead of time. So that's why that information, that instantaneous information is important. But the first part of that is the instrumentation, so you can get that instantaneous information. So if we didn't put in that little envelope in FedEx, and there's all those barcodes on it, and give it to the FedEx driver, think of that envelope. That's a big envelope. It adds a lot of weight for a little letter. But we look at the world right now as bandwidth is much more available. We're not in 56K bit modems anymore, okay? Bandwidth is much more available. Quality bandwidth is precious.
We've recorded some shows recently where people are talking about adding a new header for service chaining, which is, I think, by some calculations, it's somewhere between 120 and 240 bits. And I can remember back from 10 years ago, people who were having conniptive fits with a 53 with the ATM header at 53 bits would be turning in their graves, to be like, my God, criminals. And an MPLS tag at 20 bits. We don't care about bandwidth, really.
Well, again, I mean, there are some situations where you want to be careful about it, and I understand those. But frankly, this, again, go back 10 years ago, you wouldn't be able to do this. The networks weren't big enough to do this, right? Yes. Now, what matters, again, for our voice traffic, I can send it redundantly.
Well, let me just drill into that. Sorry to interrupt you, but I want to ask it. You're saying 10 years ago we couldn't do this sort of traffic shaping because it just didn't make sense because the bandwidth was so slow and so limited, things just weren't possible.
Exactly. The costs were too high, too. I mean, the economic underpinnings of all of this, right? Again, I go back to the Intel architecture being rather inexpensive. Memory is inexpensive. I have big databases. Hard drives, SSDs are inexpensive now.
And these are the things that power your, all this software and all this functionality. You're saying and let's just restate this just to make it clear, is the x86 with lots of RAM means you can run this software that does all this magic at a reasonable price now.
Absolutely. I have per flow tables that help me steer traffic around, and I reassemble those traffic sequences on the other side if they happen to get out of order. Those things, 10 years ago, that would have been a cost-prohibitive solution. The bandwidth would have been a cost-prohibitive solution. I mean, it just wouldn't be economically viable. But today, the world's a different place, right? We've had these disruptions with Moore's Law and, frankly, with bandwidth availability and other things like this. Now we can do these things in a much more intelligent way, taking best effort, commodity type of things, which we probabilistically measure the hell out of, and then, that can be superior than a deterministic, centrally administered MPLS or what used to be frame relay at the time network. So probabilistic with redundancy and intelligence is better than deterministic with single point of failure.
And self-configuring, autonomous,
exactly.
Limited CPU, limited memory. The routers that we know of, over the last 10, it needs to be replaced with something more sophisticated. I want to come back to my question, which we seem to have lost on, visibility. How do we see all this? How do we manage this?
Again, the policy configuration at the centralized point is important, but the other thing is we have SQL databases on each of these appliances, which stores data for a week, maybe 30 days, depending on the appliance. But that data is periodically compressed and sent to the centralized aware node, and that aware node then provides correlation. So, you ever have that link go down somewhere at that one site? Well, was it that site? Was it AT&T in the Northeast? Was it regional? Was it somewhere in the middle? I mean, quite often I've had problems where I've been prototyping and testing a preliminary product. We noticed paths going down, and we just realized Juniper had a core dump somewhere in the middle of the network. But we can detect that, and so we can immediately correlate this data. It's not just this one site, and then you're looking at this other site and this other site and trying to do it yourself. We need to bring that up into one pane of glass, and you can say, hey, look, it's red. And everybody in the Northeast is red using that service provider. It's not me. 1-800, call them up, fix it, please.
And so that central node is called aware. That is not a generic term. That is like a software branding thing that Talari has. You call it aware, and
yeah, exactly. It's a VM. It's not time critical there because it's how you configure things in an architectural way. It's also how you can analyze things, but it is not in the band of packet flow.
Yeah, right.
The network control node is the time thing. That is involved in the time synchronization and a lot of those things. So that's the two-tiered. The aware is a strategic node, and the NCN is a little bit more of the field commander.
So on that aware node, then, if I want to dig into what analytics capabilities it gives me, you've already told us some of it. It can tell me what's broken and where because it does data correlation from across all the nodes that are in the Talari network. What else do I get out of it? Like, can it tell me things about application specifics, maybe? Absolutely.
It's a little bit of convergence of the APM MPM. I know AANM is what a lot of people would call it actually now. But examples we provide MOS scores. What's the worst MOS score in the voice network in the last week, and then you can plot that across a chart. It also does event aggregation. Now again, SolarWinds and Netflow aggregators and syslog aggregators, love them. We support those things. I want to make sure that people don't think we're totally off the reservation here. We support those things. Those tools are out there and they're wonderful tools. But we also believe that our depth of data is not well served by those things. And so we provide that with this SQL analysis. It's a web-based app that you can use.
There's a gap between packet capture, flow capture, and trend, interface SNMP. There's a massive gap in the middle of those, which is, and it sounds to me that that's like more. Is that a fair statement? That's where you sit?
Absolutely, it's a fair statement. Absolutely fair statement. But let me give you an example of like a syslog or a Netflow aggregator. If you centralize the Netflow aggregator at the data center and all the network goes down in the meantime, you don't see the flows, right? Because it's chatty, right? They're not storing it on the database. With us, if the network goes down, then we reach out, a minute or two later, and then when it comes back up, and we grab the SQL database. So we have the history on the system, and so we don't have gaps in time. You can actually see what was happening when you had the blackout. And you say, oh, geez, that's what happened. That's why it happened. And so so providing the SQL as an infrastructure, again, we do all the other things everybody else does, but providing the SQL as an infrastructure provides us a better time consistency.
So, John, one thing I wanted to get into with you is how to integrate a Talari solution with my network. So, okay, I'm a network engineer, and I am used to my routers and my circuits getting plugged into my routers, and now I've got this Talari thing that I'm going to put in. Now, if I've done WAN optimization with some other vendor, let's say, I'm used to, I know what that process is like. I got to put an appliance in line and all that kind of stuff. And a lot of network engineers here have maybe done a WAN op solution in the past. Now, I know you're not WAN optimization, just trying to make a comparison with things that people are used to. So we've talked about a controller. So there's got to be a controller or with redundancy built in. There's an appliance that we've talked about that could be standard Intel, or it could be, I assume it could be a virtual machine as well.
Mm-hmm. Yes, it can, definitely.
Okay. So there's software that's then running on that appliance, and is that something I've got to maintain, or do you just kind of hand that off as like an entire virtual appliance, or it's all integrated on the x86, or is there like an install I got to go through?
Most of our use cases there's an appliance. There's a physical appliance. And actually, it's almost the exact same hardware as a WAN op hardware. It's got a fail-to-wire card or bypass card, depending on which vendor you talk to.
Oh, in other words, if it's got no power, the thing, it just passes traffic through.
Magnetic latch, click. Next thing you know, assuming you have the duplex set up right, you got to make sure you test all this stuff. And I think we all know
right.
that serial inline's got some issues if you're not careful. But again,
well, that's a solved problem by now.
Yeah, well, it does make that middle of the night installation a little longer to test every flip, every switch. But in any case, you put us somewhere behind the WAN op and then in front of the ISR or the firewall. And
your Ethernet, by the way. We're talking about putting it in front or behind. We're talking about Ethernet connectivity.
Absolutely. Ethernet everywhere. And so you put that there, and then now in terms of software install and stuff, we just like the policy centrally administered, we actually have something we call SureChange, which actually does centralized administration of software. So you don't really have to worry about. We don't have to do partition updates, for example, when you want to install software. It just you put it in there, and it automatically will synchronize the latest version of software, which it verifies against the policies to make sure everything is good, and then distributes it automatically. So those type of things are good. If it's a VM, there's a little bit more logic in the VM because you don't have necessarily the underlying fail-to-wire card. So you have to have a little more of a soft switch there. You don't always have to go in the inline mode, and quite often people don't. They can do what we call one-arm topology, which is you have an ISR or something like that, and you put us on one arm there, and you still are using policy-based routes to us. The nice thing about that is you can logically flip us in and out, and you can establish, in a sense, your service chain. But that's a little more complicated in that branch office, so sometimes it's easier just to hook up the wires than it is to do that based on that router. Depends on your IT shop.
You do virtual machine form factor, so if I've got stuff sitting up in the cloud, can I put a Talari node up in my cloud if I'm doing like IaaS or something?
Absolutely. And actually, it's a really useful case there, a really useful use case there, because when you do a mouse click and you're doing a software as a service and the mouse doesn't come back, you're kind of stuck, right? Whose problem is it? Is it the internet service provider? Is it the server up there? Is it somewhere in your enterprise? And so we view the cloud as just another extension of your enterprise, right? So you can actually put a Talari virtual node up there in the cloud. Amazon in particular is what we do today. That will still provide the same diversity of internet access. And actually, we even work with AWS Direct. And then we try our best to make sure the traffic gets there, right? We're doing everything we can to make a silk purse out of a sow's ear. But what's also important is if the network's not capable, despite our best efforts, we can't get it there. At least you know that. Information is empowering. And so you'll know where to point the finger. Is the finger in the WAN, or is the finger somewhere on the server side? And that gives people a lot of peace of mind. Our providing that conduit service and those analytics that we provide that is really very useful for them.
Now, okay, some people are going to listen to this and go, I don't want to put it in line because I don't, it makes me sad. Can I kind of have it one-armed off to the side and use, I don't know, a standard routing protocol to connect to the interface, or WCCP, or is inline really the way to go?
We do inline. Typically, we go one arm. We'll do policy-based routes. We can also do some route table manipulation to do it as well. Policy-based routes are nice because when people want to do service on something, they can just go in there in the CLI and change it and get it out of line. And then they can go back to the default primary network. Maybe it's MPLS or whatever. We do have WCCP stuff going on, but I'll be honest with you, WCCP is a pretty horrid protocol between us.
Yeah, and core switches don't do it in
I would rather
hardware very well, and it sucks. But
yeah, I would rather just go straight for the target and do SDN hooks in a virtual switch.
Yeah, I get it. Okay, so it sounds like I got a bunch of pieces of parts I'm going to be putting in. It is not unlike what you would be doing if you did a WAN optimization deployment, kind of similar, a lot of similar considerations and concerns, for like any other appliance that you're putting in line, how that works. So, and then you can use PBR if you want, policy-based routing, to swing traffic off to the side if you don't really want to put it in line. Because you could do WCCP, but yeah, it's not a lot of fun for anybody. Okay, so pretty predictable standard way to add this stuff. Oh, there's one other thing I wanted to go back to that we were going to talk about it way early on in our notes, and somehow we wandered off into the field and didn't get back to it. But that was ECMP, because you had raised an issue on your website that I'd noticed about how you guys do ECMP. You call it intelligent load balancing, and I think most of the people in this show would know that, listening to this show, would know the difference between per flow and per packet load sharing, let's say, with ECMP, because that's one of those things you can set up. And by default, you do per flow typically, but it doesn't really get much smarter than that in most ECMP designs. And when you get into ECMP over the wide area, it's a totally different thing, because latencies are far different, and so there's it's a thing, it's a concern. You typically don't do any kind of load sharing across the WAN, but you guys do this intelligent load balancing thing. And you talk about that?
Yeah, sure. I mean, again, it goes back to the underlying economics of the Intel architecture. Of the Intel architecture and memory and such. We can have more state, and that makes us able to do more things. Let's assume we got 3 paths going across the network, right? 3 WAN paths that were combined into a conduit. Each one of those paths may have a different latency. Let's say one's got 20 milliseconds latency, one's got 40, one's got 60. And then I come in, I'm doing a remote desktop, and I do a mouse click. Well, I don't want to load balance that mouse click across all those links, right? I think I said 10, 20, and 40, right? So it should just take the 10 millisecond link, the 10 millisecond path. Let's say then I do a file transfer, but it's not that much of a file transfer. Maybe I'm pulling a web page or something down. Maybe it's enough to saturate that 10 millisecond link, but it kind of spills up into, and I buffer it up a little bit because I'm using the 10 millisecond link, then it will spill over to the 20 millisecond link. Well, I don't need to use the 40 millisecond link, because it's not saturating enough, right? So this is latency-aware balance. I don't round robin, because you go from the 10, 20 to 40 and then go back to the 10 again. Well, that fourth packet's going to have to wait for the third packet to show up, and that's going to cause some bad things. So what we do is we are aware of the one-way latency, and we can fill in progressively and then spill up to the higher latency paths based on the use case for a single session. The thing about this that's good is that when the packets arrive at the destination node on the far side of the network, on the off-ramp, that they come in in sequence. Now, we do have a resequencer over there, right? Again, taking advantage of lots of memory. We have a resequencer over there that will put them down together. But they come in semi-sequence. It's like QSort, right? QSort works better if it's semi-ordered. Well, when these packets come in semi-ordered, they line up real quick. There's not a lot of egress processing time, and we can let them go down the line. So we can take a single TCP stream, all the network bandwidth that we have available, but we'll only use it up to the use level that TCP requires, and we won't actually take it to the higher latency networks if we don't have to. But if they do need it, let's say we're doing rsync, then we'll use all the bandwidth and have the higher latency. But that latency is not really a bad problem for the rsync, because frankly, you just need more bandwidth. Does that make sense?
Yeah, well, I think you definitely filled in the part about the intelligent load balancing, because you are sensitive to the amount of latency going across those links. It doesn't mean you're going to throw them out. You are going to use them, but you're going to do them in such a way that the latency is accounted for. And then when you got to the semi-ordered, that filled in the rest for me, because that, of course, is the big concern with doing per packet load balancing is, but then if one line's got different latency characteristics than the other, packets arrive out of order. Now there's a burden on the TCP receiver to reorder those packets and put them back together, which is a problem. That's a CPU intensive process, especially if you're throwing a lot of out of order packets. Well, you guys are also taking the burden of TCP reordering on yourself with your own algorithms, meaning even if packets do arrive out of order, it's not like the TCP receivers got to worry about that, because you guys are taking care of it, and the receiver's going to receive them in an ordered fashion. So yeah.
And because we stick in our own envelope and we sequence and timestamp both at the application and at the WAN path level, but this is particular at the application flow level, the session level, I can do this for UDP too. And so it comes down to, I put it in the FedEx envelope and I send it across the way. On the other side, I put them back to order. I call it the Humpty Dumpty algorithm, by the way. That's my language for it. But
it's always got to have a name. So Humpty Dumpty.
Yeah, well, no king's horses, no king's men. I mean, come on, we'll get together again. So what's important is that we reconstruct the stream pretty darn close to what it looked like when it came in came into the WAN. We want to make sure that same sequence goes out in the WAN. We don't want to hurt anybody downstream, right? We're just trying to be good citizens down there. They don't have to worry about reordering because I took care of it from. But I can do it because I'm a network node with a lot of memory and some pretty nifty algorithms there that can do this very efficiently. And it goes back to, the gravitational constant in the universe sometimes it's not constant. Most of the round-robin things out there, link aggregation, bonded T1s, for example, they all assume exact same timing on links. For me, equal cost is what ECMP is, right? It's got to be equal cost. I'm sorry. The typical load balances are equal cost. We don't think that. We think they're actually different costs, and therefore we situationally balance around that. Lower latency links, then higher latency links, then higher latency links. But making sure they all stay in sequence.
Cost routing, but you're also balancing out on topics like latency, and not just some arbitrary metric between two locations. You're dynamically changing the value of the cost calculation by saying latency, jitter, bandwidth, round trip time, whatever it is, the metrics that you want to use for a given. And even then, I guess you're saying, even though my round trip time might be, so you're saying this jitter is varying wildly. There's a second's variation in the jitter, say, for hypothetically.
Exactly.
Well, it might be better to actually send this down a path that has, 750 milliseconds of round trip time, but the jitter's down under 250 milliseconds. Therefore, but only in the context of this application. This traffic type is jitter sensitive. Therefore, I'll send it down the low jitter path, even though it's got lesser, is slower in some, in terms of round trip time.
Yeah, our statistics engine that we run, the WAN egress node, i.e. the off-ramp node, is the really brains of the operation, and he tells the WAN ingress node how to, what the network map looks like. But that actually will do things where it will detect instability, even gradually. It actually has got 3 or 4 anticipation models, and it competes them. It's like weather models, right? Where's the rain going to come in tomorrow? You got 3 or 4 weather models to try to figure out which one's best.
Anticipation models. You're actually saying
exactly.
You're not actually predicting. You're anticipating, which is there's a subtle difference. Yeah.
And so we compete them against each other. We actually call it the fratricide algorithm, but we compete them against each other to see which one is most predictive, and then we'll use that to tell the other side of the network, what's the best way to send stuff across the network. We do this real time. Now, I'm not trying to figure out the weather next week, though. I'm only trying to figure out what the network's going to do in the next 100 milliseconds or so, and it's pretty darn good there. Next week's weather, not so sure. 100 milliseconds.
Next week's network traffic report, weather report, traffic weather report.
Exactly.
Let me say that again. 3, 2. Next week's network weather report is not trying to be predicted here. You're trying to predict it 100 milliseconds, 500 milliseconds into the future.
Exactly. And so when I see something get a little wonky and it's not fitting within one of my models, then I say, yeah, it's unstable. I should avoid it, even if it's a lower latency. I'm going to let him kind of stable out a little bit before I start putting some critical traffic on there. I may put some non-critical traffic on it, but critical traffic, let's kind of avoid it for now.
It reminds me of that joke with 3 Irishmen, but maybe this isn't the time to tell it. Well, I think that's just about where we should end it up for today. John, please tell people where they can find out more about Talari.
Well, feel free to go out to our website at www.talari.com. That's TALARI.com. And just click on some of the buttons there, and they can grab information and see some videos, and if they want to, even ask for us to reach out to them.
Fantastic. Mr. Banks?
I am at ECBanks on Twitter, and ethancbanks.com is my blog, and appreciate it if you'd follow me. And I've been writing a lot about SD-WAN lately, and you can find some of my posts there.
And, of course, I'm Greg Farry. You can find me on my blog at etherealmind.com and on the Twitters as at etherealmind. That's a wrap for this week, and thanks very much for listening to Packet Pushers. We should be back again in a week or so. Make sure you come back. I'd like to thank Talari for sponsoring today's show and getting a deep dive into SD-WAN technology. And you should be starting to see, just to make a couple of quick comments, you should be starting to see some patterns emerging about how this technology and how the different vendors are coming together. And Talari is different from the others. They've got some unique features around them, and you should be talking to them. And when you do, please tell them that Packet Pushers is where you heard about them, because it helps them know where they should be going to next, and it helps us to continue to bring you the content that you're listening to today. We'd love to hear your feedback about today's show, so send an email to packetpushers@gmail.com and feel free to let us know what you're thinking. You can also check out the website at packetpushers.net. Leave a comment on the blog post that accompanies this audio. You can leave questions there, and we'll make sure that the vendors get back to you as soon as we see the comments and questions and get them back to you. But you can also follow us on Twitter as at packetpushers and other fine social media institutions, but Twitter's really where we're at these days. And as always, remember that too much networking would never be enough.